In this video, we are going to continue looking at how to write proofs in mathematics with a very famous technique called doing a proof by contradiction. So, thus far, what we have looked at are examples of direct proofs, where we start with the hypothesis P, we do some math with P, and we arrive at the conclusion Q. That's called a direct proof because you show that whenever you have P, you must also have Q. We've also looked at doing an indirect proof by instead proving this statement's contrapositive. So we did several examples in a previous video that not Q implies not P is another way to prove that P implies Q. It's indirect because you start with not Q, but the contrapositive is logically equivalent to the original statement, so that's another way to prove that P implies Q. Contradiction is a little bit different. It's also an indirect proof. But what we are going to do instead is say, let's prove that P implies Q by instead proving that it couldn't be the case that P didn't imply Q. So it's like, if it weren't the case that P implied Q, something strange would have to happen. You'll see examples what I mean by something strange in a moment, but let's talk through the idea of saying it must be the case that P implies Q, because if it weren't, something strange would happen. What we need to do logically is negate the implication that P implies Q. So I'll do this not symbol. I kind of go back and forth between this one and the tilde. If it's not the case that P implies Q, then that would mean that it would be possible to have the hypothesis P without having the conclusion Q. Negating this implication means that the hypothesis does not always lead to the conclusion. So you can have P and not Q. I like to think of this as characterizing a counterexample to the implication P implies Q. So when we do a proof by contradiction, we say, imagine P and not Q. It's not an implication, it's just a characterization of what it would look like to say that P doesn't imply Q. In other words, it's a characterization of a counterexample. And then the flow of your proof will vary based on the scenario, but what we'll see happen in all three of the examples that we will do in this video is that we will say property A must hold. And then later in the proof, we'll say property A must not hold. And then we'll recognize that we've contradicted ourselves. And therefore, this scenario could not happen. We would never be able to generate a counterexample by finding P and not Q for an object out there. So it's like, by contradicting ourselves, we show that the original implication must hold. Our first example is one of the most famous proofs by contradiction. This is often presented in this type of discussion. In fact, when I was a student and I learned how to write proofs by contradiction for the first time, this was one of our examples. We want to prove the statement that the square root of 2 is irrational. In the past, we have recharacterized that using if-then language as if x squared equals 2, then x is not a rational number. In other words, if x is rational, then we could write a over b, where a and b are both integers, b is non-zero. So a rational number is one where you can express the number as a ratio of integers. Also, rational numbers have a property, if you look at their decimal expansions, that, eventually they fall into some kind of repeating decimal pattern. To say that x is not a rational number means to say that this is not the case for x. So rational numbers are defined as ratios of integers or as decimals which eventually fall into a repeating pattern. Irrational numbers are all of the numbers which do not make these statements true. All right, let's take a moment to pause. And what I would like for you to do is identify P and Q. They're pretty explicitly given here with this if-then characterization of what we'd like to prove, but then take a moment to also write down not Q and not P. So when I come back, I'm going to have P, Q, not Q, and not P. Those two senses of direction are the types of proofs that we've already seen so far. So P implies Q would be a direct proof. Not Q implies not P would be a proof of the contrapositive. What I would like to do is talk through why neither is a good idea for this statement, and then we will say what we get from setting up a contradiction. As expected, P implies Q looks just like the statement we have here. So if x squared equals 2, then x is irrational. Let's think about this first. So what if we wanted to prove this directly? I could say, all right, x squared equals 2. I like that I know what x squared is. Equality is a nice thing to have. It's very specific information. But then what? Okay, x is the square root of 2, or negative square root of 2. And this is the number we're trying to understand, but I can't really do anything with this. It would be hard to show that a number is irrational because an irrational number does not have a specific form. So it's not like I could start expanding the decimal expansion of square root of 2 and say and just trust me, if we kept going, we would never find a repeating pattern. So it's going to be really hard to just work with this and get irrationality directly. Okay, so let's reject a direct proof. Thinking now about perhaps proving the contrapositive, what we would want to say is if x is a rational number, then x squared is not 2. It's one of the infinitely many numbers which is not 2. So this is very specific. This is a bit vague, kind of like we had a specific piece of information over here. Okay, so what do we like here? We like not Q. If x is rational, as I said a moment ago, that means it can be written as a ratio of integers. That is a very specific piece of information to have about x, okay? And I'm thinking about squaring it. I can tell you what its square is. It's also rational. In fact, it's a squared over b squared, integer over integer. I am going to struggle to know from looking at this that this number couldn't be 2. Okay, so I think the contrapositive in some ways is better than going directly because I like this better than this, but I feel like I still don't have enough. What if I combined everything I liked about these two sides? I liked P, I liked not Q. Both pieces of information gave me a lot. So I knew what the square of x had to be equal to, and I knew a specific form for x. So direct proof relied on being able to take P all the way to Q, like start with P, end at Q. An indirect proof by proving the contrapositive required me to go just from not Q to not P. If I take P and not Q, I get both of those. So in some ways, a proof of a proof by contradiction gives you a lot to jump off with. All right, what I'm going to do is just kind of play around with the scrap work here, and then I will put up a fully written proof in just a moment. So let me imagine brainstorming for a second. As we did in the past, let me imagine that I'm working on scrap paper, and I'm just trying to see if I can take P and not Q and get somewhere productive with it. The thing about a proof by contradiction is that you don't always know exactly how the argument will follow. What you're looking for is having an idea, maybe usually at the start of the proof, and then realizing that you have the exact opposite of that later. Okay, so I will imagine now that I'm just going to play around with P and not Q. Since x is a rational number, we know it can be written as a over b, where a and b are integers, b is non-zero. And I know that x squared is 2. So let me just go ahead and say a squared over b squared is 2. This is just scrap work. So in the formal proof, I'm going to introduce a and b so that the reader knows exactly what we're looking at here. But this is me kind of experimenting with the ideas that we are going to start our proof with. Okay, well, I see a fraction. The most natural thing to do is bring the b squared over. So I could say, all right, a squared equals 2 times b squared. What does that tell me about a squared? It's twice an integer. So we know that that means a squared is even. Okay, so it implies that a squared is even. We proved by using the contrapositive in a previous video that if you have an integer and the square of the integer is even, then the original integer is even. It's not a very hard thing to believe, right? So even integers squared are even, odd integers squared are odd. But we did literally prove that if a squared is even and a is an integer, then a is even. Okay, so I can say more about my representation for x. My numerator, a, is even. All right, so that means that a could be written as 2k for some integer k. And again, I'm not going to write out all the introductions in my scrapbook. I'm just experimenting. Let me bring this 2k over here to this left-hand side and imagine substituting it in for a squared. 2k squared will give me 4k squared, 2b squared. All right, divide both sides by 2. So I'm going to also flip it. B squared equals 2k squared. But wait, that means that b squared is even. B is an integer. B is an even integer. All right, so from this, I'm getting b squared is even. And therefore, b is even, just like we did above. There is a problem here, and before I state it out loud, I'd like for you to have the chance to see what's going wrong here. So ultimately, these two conclusions we've reached are going to allow us to set up a contradiction, but take a moment to see if you spot it. The heart of this proof relies on the fact that every rational number can be put into what we call reduced form. So if I have a over b, and let's just imagine that x is the number 1/2, I could say, 1/2 is 2/4, or it's 7/14, or -50 over -100. You know this. There are infinitely many ways to present a ratio of integers which equals 1/2, but you can insist that the ratio of integers that you're working with is in reduced form. Right, so if I had 2/4, just divide the top and bottom by 2, get it to the point where, say, the greatest common divisor of a and b is 1. That means every rational number can be put in a form where it's not the case that both the numerator and denominator are even, because you could divide by 2. And if after dividing by 2, they were still even, divide by 2 again. Eventually, you can get it down to at least one of the two has to be odd. And yet here we're saying that if you have any fraction which equals the square root of 2, so any form a over b for this number x, it has to be the case that both the numerator and denominator are even, and that's a contradiction. So you could reduce this down and have one of the two at least odd. Okay, so that is the contradiction. What we will need to do in our proof is introduce x. So we'll say, suppose that x is a rational number whose square is 2. Since x is rational, there are integers a and b out there, b non-zero, so that x equals a over b, and it's not the case that both of them are even. I don't think I'm going to use the language of greatest common divisor, but you could say, GCD, greatest common divisor of the numerator and denominator is 1, so that it can't be reduced further. So we will introduce x by saying we have found the best representation for it, if you will, the one which is fully reduced. And then we will come over here, do this, just, in words, realize, no, wait. We're now saying that actually both are even. Our fraction couldn't be reduced, even though we said that it was, and that's the contradiction. Okay, think about this for a moment. This argument, or this proof, I've seen it upset students in the past, partly because they feel like, okay, well, isn't it okay if they're both even? Can't you then just divide by 2? And again, realize that what we're saying is any fraction that you provide for x cannot be in reduced form. When I come back, I'm going to have the fully written out proof. That's the case because I tried to do this on the board and I ended up running out of room and it got really messy. So I'm just going to give you my write-up for this proof, and we'll read through it together. I want to highlight a few key phrases that improve the readability of the proof, and then we'll move on to example 2. So here's a full write-up that the square root of 2 is irrational. Sticking with conventions, I'm opening with PF and closing with this box down here to tell my reader that the proof starts and ends in specific locations. I want the reader to follow. I don't want to be mysterious. So I'm opening also with the phrase for the sake of contradiction. That's something that I like to say whenever I prove by contradiction so that they know that what they're going to read doesn't sound like P implies Q. So anytime you're proceeding indirectly, make it really clear to the reader what's going on because otherwise it's going to throw them for a loop. In addition to mentioning that as contradiction, here I've spelled out what the correct starting point for this proof is. So namely that x is rational, that's actually not q, and that x squared is 2, that's p. The rest of this first paragraph here, I'll leave you to really read through it, but that is just saying that since x is rational, it can be written as a ratio of integers, a and b, just like we saw before, so that a over b is in reduced form. This is a very famous proof, so other versions of this proof might include a note that the greatest common divisor of a and b is 1. What I'm going to do instead is point out that if it's in reduced form, they can't both be even. Okay, and then paragraph 2 is all about how if a over b squared, or in other words, a squared over b squared is 2, we can work out of that a itself is even. Notice that I am in the middle of a narrative about proofwriting, and we had an earlier result that told us that if an integer squared is even, the original integer was itself even. If you are building up a sequence of results and you are using an earlier result, cite that. It's always nice to say where your knowledge has come from. So if you've got like a narrative of results, do call back to earlier results. It's in a textbook or write-up. You might even have some kind of numbering system. For us, it was like the previous video, so I'm just going to cite that. Okay, and then I bring in what that gave us and basically reach the same conclusion about B. B is also even, and therefore we have a contradiction because earlier I said they couldn't both be even, and now I'm saying A is even, B is even. That's a contradiction. I will give you a moment to pause and read through this. Let me explain the coloring system here. So I would say that every required statement here is in white. And then all of the orange phrases are phrases which could be optional. Maybe you don't need to spell out for the reader that they're not both even. Saying that it's reduced is enough. But to increase the readability of your proof, I think it's nice to include all of the orange phrases. So my orange phrases here are perhaps optional. You can be really terse and kick them out of your proof, but I don't think that there's any benefit to doing that. Part of being good at math, science, really any subject is communicating it. And so I want the reader to follow the proof. And so I like to include these kind of guide phrases that take them from the start to the end. Let me step aside and let you read this. And when we come back, we will do another very famous proof by contradiction. Here's our second result, that there are infinitely many prime numbers. This is another very famous proof by contradiction. Although I want to have a little bit of a discussion about using that technique at the very end, together with some historical remarks. We have taken this thing that feels like a fact, the set of prime numbers is infinite, and broken it down into an if-then statement so that we can recognize what the hypothesis and conclusion are. This is one of those statements that almost feels axiomatic, but it's not at all, right? So the structure of prime numbers really needs not just investigation, but also rigorous support whenever you want to make this kind of statement. Just like we did with example 1, take a moment to write down P, Q, not P, so that we can talk about what it would look like to proceed directly, indirectly by addressing the contrapositive, and then ultimately with contradiction. Based on the if-then phrasing that I put at the top, this could be P and Q and not P. So if S is the set of primes, then S is an infinite set. It has infinitely many elements. Versus if S has only finitely many elements, then S cannot be the set of all possible primes. Unlike example 1, there are many ways to prove this, or at least there are a few ways to prove this, and you could actually set up a direct proof and a proof of the contrapositive. We will talk about that at the end of this example. I don't want to kind of start doing different arguments all at the same time. So let me go straight to contradiction and why I think of all of the approaches we could take, it's the one that feels the most straightforward. So it's the easiest, if you will. If we assume P and not Q, then I know that S has all of the primes. I'm not missing anybody. So that's a powerful thing to know about S. No prime has been left out. And I also know exactly how many primes are there. It's some finite number. So again, P and not Q are in some ways the most specific, and pairing them together gives me a concrete way to say what the family of all possible prime numbers looks like. So let's say S is P1, P2, all the way through P sub, I'll do capital N to represent some finite number. So if there are 50 primes, capital N is 50. So this presentation is how we will open our proof. We will say, imagine we can list out all of the prime numbers and they form this finite collection. The rest of the proof is a little bit trickier than number one. So I like number one because once you've written a squared over b squared equals 2, I think it's natural to bring the b squared over and just the algebra starts to happen. Here, the next step is a little bit more of a jump. I don't know that I would ever come up with this on my own. Euclid published it in the Elements over 2,000 years ago. I think it's really clever. If we were going to try to come up with this for the first time, how could we possibly get to what I'm about to write down? Well, we can do algebra on finite collections of numbers, right? We could add these up and we would know it added up to a finite number. We could multiply them together and we would know that we would multiply them to a finite number. So having a finite group of numbers means that we can do explicit computations with them. When we think about prime numbers, what computations come to mind first? Well, prime numbers are only divisible by 1 and themselves. So 5 is only divisible by 1 and 5. That's what makes it prime. Whereas 6 is divisible by 2 and 3. So it's not prime. And in fact, 2 times 3 is what we call its prime factorization. Okay, so the operations that should come to mind if you're looking to work with this group of prime numbers are multiplication and division. So then it's like somehow we need to come up with a contradiction. We're looking to say that there's a prime number out there which isn't in this collection. In other words, by me saying, hey, here are all the prime numbers, they're just finitely many, and you saying, no, there's another one that you're missing, it suggests I cannot collect them all in this finite way. So how do we make a number which isn't in this list, but which is prime? Or how do I know that there's a number missing here? And again, the most natural things to think about are multiplication and division. From this list of numbers, multiplication would give us a construction. So it's like I could take all these numbers and start multiplying and I construct something. So what if I took the product of all of them? Well, that is not at all prime because it's divisible by every single prime on this list, like how 6 was divisible by 2 and 3. But if I take this number and add 1 to it, let's call this number x. Now what I'm saying is that this new number x is not divisible by any of the primes on this list. I'll tell you why in just a moment, but take a second to see if you see why. What happens is that x is not divisible by p1, say because if I tried to divide it by p1, it would be p1 times the rest plus a remainder of 1. So this is like a remainder after division by any of these primes. You can compare it here to 7 equals 2 times 3 plus 1. We have to be a little bit careful about what our conclusion is. Looking at this, you might be tempted to say it's a prime number itself. 7 is certainly prime, and we can write it as 2 times 3 plus 1. But it actually doesn't have to be. It may be prime, in which case, great, we found a prime number which is not on this list. We know it's not on this list because it's larger than all these numbers, right? Certainly not even divisible by itself if it were on this list. So it's possible that x itself is prime, but it could also not be prime and yet have a prime character or prime factorization which includes primes not on this list. So there are really two ways from this new number to to generate a new prime number. Either this is itself prime or it has a prime factor, which we know can't be one of these. Okay, I think coming up with this is more advanced from a point of view of like what next once you've set up the contradiction than our first example. But I hope it makes sense to you how starting with the assumption that we have a finite number of prime numbers leads us to a contradiction. We can generate a number which is either prime itself or has a prime factor not on this list. So that's the contradiction. And if you get that, great. The focus for the rest of this example, of course, is actually on writing this up. Just like with example 1, let me put up the entire thing and I'll just talk you through it. And then I want to take this example a little bit further. So here's a formal write-up of what we discovered in our scrap work. If you look at it, it's almost exactly the scrap work. So there's not anything here that I didn't say out loud or write down a moment ago, but it's a nice presentation. It takes the reader from the beginning to the end. So when you write a proof, it's not just about having the idea and saying, well, here's my scrap work. You also need to communicate it well. So in the usual way, I start with PF and then I have FTSOC here. That's for the sake of contradiction, just to save a little room. The rest of my first sentence is Pn, not Q. So suppose that there are only finitely many prime numbers, and then I present a way to collect them together in a collection I'm naming S. Okay, and then I bring in this number X, kind of centered it on its own line to really emphasize its importance. My orange by construction phrase here is different from my orange color coding a moment ago. I just wanted to point out that I'm using a phrase I write a lot in proofs, but which I don't think I've used before. For me, by construction means I'm about to say an important property, and the property is not based on something mysterious. It's literally based on how the object above, which is this number X, was built. So it's like if you're the reader and you read this phrase, I'm telling you where to look for this information. It's in the construction of X. So look at X, and you should see that the following property holds. I did spell it out for the reader, though, which I think is the right thing to do here. Don't just say X is not divisible by any of the primes from the set S. Take it a little bit further and say that because if we tried to divide it by any of the primes from S, we would leave remainder 1. So this proof isn't that long, but I don't think it should be much more terse than this. Okay, and then I covered the two cases. Either X is itself prime or its prime factorization would have to include a prime not from S. I think we've already talked through that. So here you can just see me writing out those ideas. And then since this is an indirect proof, the flow of the proof doesn't perfectly match the statement that we were proving. So here I have put in like a summary statement, just taking the reader back to the original goal, which was to conclude that there are infinitely many prime numbers. And that's it. So again, this should sound exactly like our scrap work. It's just a nice presentation of it. Take a moment to read through it, and then we are going to take this proof and just alter it a little bit. Just like example 1, this is a well-known, very famous proof by contradiction. I think if you stopped a mathematician on the street and said, quick, name some famous proofs by contradiction, they would say both of examples 1 and 2, or many would. However, I would like to take the proof we have here and present another version of it. So here is almost the same proof, but there's a little bit of difference. Take a moment to read this and see what you make of it. This proof follows the same train of thought as the first one. I said, consider this finite collection of primes. Look, because of this number X, I know this finite collection doesn't have all of the primes. But this is not a proof by contradiction. This is actually a proof of the contrapositive. If S is a finite set, then S is not the set of all primes. And if you think back to contradiction, we never really needed in our proof that S was all of the primes. What we were really focused on for the rest of the proof was that S was just a finite collection. And that happens sometimes. You start with contradiction, P and not Q, And, perhaps the first draft really uses both of them, but maybe as you refine the argument, like this could be seen as a refinement of the earlier proof, you actually realize that you've dropped P. And what you're really doing is contrapositive, or maybe you've dropped not Q and it's actually direct. So I would say that this is a proof by contrapositive, and I believe that this is actually closer to the proof that's in the Elements, Euclid's famous text from over 2,000 years ago, but I actually haven't looked at it recently. I think that the actual proof is more along this line than a strict proof by contradiction. Okay, I just wanted to point that out to you. I don't think it's bad to set this up as a proof by contradiction. If I did, I wouldn't have done it. Certainly, working with P and not Q eventually got me there. And again, maybe just on a final version, I recognize that I can just take it a little bit further to write something which is perhaps a little, I would say a little bit more sophisticated. I think I like this proof better than the first one. Okay, our final example will not be one of these like grand statements from math, but I do want to look at a common context in which we use contradiction. I've labeled our third example as coming from linear algebra. If you haven't had a formal course on linear algebra, but you've worked with matrices before, I think you'll be just fine. This is not a very advanced statement from linear algebra. When it exists, so when a square matrix is invertible, the inverse of that matrix is unique. I've put here the definition of a matrix inverse. It's like a multiplicative inverse where the identity matrix is our famous matrix with all ones along the main diagonal and zeros elsewhere. If you know that, then you'll be okay for the rest of the example. If that's completely unfamiliar to you, still watch, because what I would like for you to take out of this is that often in mathematics, when we look at special elements, we discover neat objects, functions, multiplicative identities, that sort of thing. We wonder, is it the only one? So the question of uniqueness often arises in mathematics. And if we want to prove that something is unique, we often approach it by saying, well, what if there were two? So what if it wasn't unique? And then we see if that perhaps is a contradiction and we can get to uniqueness that way. Okay, so to wrap up, again, do P, Q, not P, and then we will have a pretty fast proof of this statement. The original statement was not exactly phrased as if P, then Q. So here are P and Q. If A is invertible, then A inverse is unique. Then here are not Q, not P. I had a debate with myself about not Q, because if you're saying it's not the case that there exists exactly one, it's either zero or many. But I left off that there's no inverse whatsoever. That's actually a tautology. If there is no inverse, then A is not invertible. What we really want to focus on for this proof of uniqueness is a situation where you have multiple inverses. That's what we want to rule out. So if there are multiple inverses, we'd like to say that that is going to lead to a contradiction. So if A has multiple inverses, then A is not invertible. It's a very strange sounding implication, but it's actually true. So this not Q implies not P. This is an example of a vacuously true if-then statement, because the premise or the hypothesis, this is never true. So it's like this statement, it can only be false if this is true without having this, if this does not always lead to this. But if the premise, if the hypothesis is never ever satisfied, we actually say the statement is true. So the original implication is true, as is the contrapositive, but it's sort of a funny thing to read. I think the most natural combination here would be to try P and not Q, because it's like if we're going to have multiple inverses, we are going to be assuming anyway that A is invertible, right? So as soon as we say there's more than one inverse, we've got this kind of implicitly. So let's just go ahead and deliberately bring it in. So let me do some scrap work here, which is going to lead to a very short proof. Let's imagine that there are multiple inverses. So what if AB equals BA equals the identity matrix, and also AC equals CA equals the identity matrix? I'm being kind of bad with my handwriting here. Sorry, I'll also switch to green. Let me just take one of these expressions. How about AB equals the identity? then what happens, I think I've lost a marker. Okay, I'll go back to pink. Well, what if I just took this and hit it from the left with C? And then it's like C times A times B equals C, but actually CA is the identity. So we end up with B equals C, and therefore we're going to conclude that B and C couldn't be distinct. They are in fact equal. I will just want to again reiterate that whenever you're looking at a question of uniqueness, try at least this type of experimentation. Your proof might not always be an exact proof by contradiction, but anytime you're like, is it unique? Could it be unique? Just throw out there the idea that it's not, and that you have multiple instances of whatever you're studying, and just see, maybe you'll conclude that actually they have to be the same. Okay, I'll put up a very fast proof of this, and then we'll summarize what the types of proofs that we've looked at so far, so both direct and the two indirect styles. All right, here's the proof. So for the sake of contradiction, suppose that A is invertible, that's P, but B and C, which are not the same, are both inverses for A, so that's not Q. And then I basically just put my scrap work here, but you'll notice that I was a little bit more careful with my matrix operations. I don't really want to cross out matrices. And also, I really like, whenever I'm trying to go from one idea to another, I really like freezing one side and going down the right-hand side. So even if this feels a little bit more artificial than the computation that you may have done on scrap paper, I just think it's like very nicely presented. Here you can see I used matrix associativity, so I try to be very correct with my matrix operations there. Notice that when I write proofs, when anyone writes proofs, you really want it to be proper writing. So I've got complete sentences. I don't like starting sentences rather with math symbols. I don't think it looks very nice. And even this computation, which on scrap paper would stand alone probably, it's still part of a complete sentence. Sometimes it's as simple as just throwing the word observe or notice or we find above the computation. So you're like, observe math. And then, I put a contradiction at the end, but I could have also just put a period here. It's on there. So, everything should feel like part of a complete train of thought. And as usual, I have tried to highlight what the contradiction is, wrapped up the proof pretty nicely. I think this is a nice short proof that a matrix inverse is unique. I just want to take a moment to summarize the three approaches that we've seen to proving an implication. The first is direct. Prove an if-then statement by literally saying that from the hypotheses, we arrive at the conclusion. Whenever possible, I like direct proofs because they mirror the original implication, and I think if you can show how the hypotheses lead to the conclusion, it makes the result feel very natural. If during your brainstorming session, you find yourself continually saying, well, if it weren't the case, and if it didn't happen, meaning you weren't getting to Q, if you're trying somehow to say, no, we won't get to Q, then maybe what you actually would like to do instead, or maybe need to do instead, is an indirect proof. So the two approaches for that are via the contrapositive and contradiction, as we've been discussing in this video. They're different. They're both indirect because you start with not Q. It almost feels like working backwards compared with a direct proof. Notice that both direct proofs and proofs of the contrapositive statement are still implications. So if you prove the contrapositive, you're still starting and showing that you're getting somewhere. I'm not sure if I said that well, but it's like this just becomes your new hypothesis and this becomes your new conclusion. So you're rearranging the original statement, but it's still an implication that needs to begin somewhere and end somewhere. A proof by contradiction is a little bit different because basically you just say, imagine this, which as I said in the beginning, it's like describing a counterexample. And then you're basically saying that counterexample could never happen because it violates the laws of mathematics. We arrive at some kind of contradiction. So there's some logical inconsistency in imagining this scenario could ever exist. So it's not exactly an implication. It's more like start with an assumption and then just show that something breaks down along the way. Look at the similarities from where we start. So here we have P, here we have not Q, and here we have P and not Q. So in some ways, a contradiction, approaching a proof from the contradiction through the lens of contradiction, let me put it that way, feels like it gives you the most to work with because you get both this and this. If you are doing a proof by contradiction, it's worth taking a moment to reread your proof and verify that you really did need both of these pieces, because sometimes you don't. After some refinement, you might realize, no, actually, all I ever needed was not Q, and I could do this by contrapositive. Or maybe the best case scenario is all I really needed was the hypothesis, so I can write a direct proof that mirrors the original implication. Okay, I will wrap this up here. Thank you for your attention.